Are you finishing your master's degree or?
Yeah, I'm a master's student, not a PhD student.
You're not PhD?
No.
No? No. Oh, I have too many mistakes. Hello, everybody. This is another Kent seminar, and today we'll have two presentations. Again, one of our sessions that we have ICT projects that was presented in TRB. So one of the presentations, the first presenter is Jeff Lahusik, and he's working with Professor Rösler in his research group. He's a master's student, and then he's finishing his master's degree soon in May. His presentation is about roller compacted concrete with macrofibers. And the second presentation is about non-destructive techniques used for evaluation of full-scale reinforced concrete. And Haijin Choi will make the second presentation. So let's give a round of applause for Jeff to get his presentation started.
So I'll be talking today about roller compacted concrete with macrofibers. I know it's a little unique to have concrete here up at Atrial, but bear with me. First, I'd just like to thank my co-authors, Sachin, Professor Rösler, and Armin. So a little background to RCC and what it is. It's very similar to asphalt concrete in terms of its construction process. So you'd use a paver, typically a high density one, and then come back behind it with a vibratory roller, and then smaller steel wheel rollers to just kind of flatten out that surface, get it smooth and tighten it up. So in asphalt, you have to worry about your heat, and that controls your timing of compaction. With RCC, you have to worry about the cement hydrating and solidifying, and that kind of controls this time on compaction. So typically, it's compacted within 60 minutes or so of mixing. The resultant product is very similar to conventional concrete. It has similar compressive strengths, flexural strengths, and shrinkage properties. So with less cement, as we see down here, a little bit less cement. The main difference is we have much more aggregate content in RCC than in conventional concrete by reducing our water and air. So the resultant densities of RCC is significantly higher than normal concrete, and this kind of gives us better properties as well. And it is typically historically been used for industrial pavements in facilities where we have high wheel loads and very slow-moving traffic. One, because RCC is very strong material, can hold up to these loads, and also because it usually has a rough surface due to it being rolled as compared to normal concrete where you just pave it and you can get a very nice smooth surface. Lately, they've been moving towards using it on highways, city streets. Mostly it's been capped with asphalt, but they're starting to get away from that and starting to leave it as an exposed surface by coming back and diamond grinding it. So it's evolving. It's gaining much more interest due to its cost effectiveness, due to lower material costs, particularly cement, as well as the fast construction. You can typically open this to traffic within, to car traffic within a few hours, and to truck traffic within a day or two, as compared to concrete where you have to let it sit and cure for 14 days or so. So the motivation behind putting fibers in this is that the main deficiency of RCC is that we don't have steel across joints. So we can't put tie bars and we can't put dowel bars, which can hinder our load transfer across joints, and we rely on those in conventional concrete. So a previous study a little while back on RCC, they found load transfer could be as low as 20%. So that is significantly increasing your stress on corners and edges. And we know from some of Professor Rösler's research and slabs that are still out in the Atlas yard that fibers can increase, or not increase, but at least maintain that load transfer over time. So that was the main reason we wanted to look at using fibers. There's also some other benefits. It can keep your crack widths tight. So when you put a asphalt overlay on top of it, you don't get reflective cracking quickly. And we can also, by doing residual strength testing, we can account for that and reduce our thicknesses. And then it's also been shown to lower crack deterioration rates, so it will maintain those joints over time. So I'm not the first one to research this. There's been previous studies on fiber reinforced RCC. Most researchers have focused on using steel fibers. A few have done synthetic fibers, one of which they basically took old milk cartons and cut them up and tried using recycled plastic. And across the literature, there's been very conflicting results. People have shown that strength and moduli have increased. People have shown it to be the same. They've shown it to decrease. In terms of normal concrete, fiber reinforced concrete, we would expect strength to be similar or even slightly lower. So there's a wide array of properties that one would expect from the literature. And so far there hasn't been any flexural performance testing, flexural toughness testing, according to ASTM C1609, which is really where you see the benefit of these fibers. And there's also there's been one study on fracture testing of fiber reinforced RCC. So this is kind of a table summarizing the results from the literature. As I mentioned here, we see for compressive strength, there's just a wide array of resulting properties compared to non-reinforced RCC. This is, a factor of mix design, a factor of what kind of fiber was used, a factor of the fiber dosage, what age specimens were tested at. So same thing for flexural strength, variable results, increasing, decreasing. So we wanted to kind of go into this and see what the actual effect of these fibers would be. So our objectives was, first off, we wanted to fix the mix design so that way we can control that variable. So we fixed the gradation and the cement content. And then from there we chose 6 different fibers to use, so that way we could look at the effects of fiber type, steel versus synthetic, as well as the effect of the fiber geometry. So whether it was a smooth fiber or it was deformed and it had some surface texture to it. And then as well as fiber dosage, so how many fibers we're putting in there. And then some of the properties we measured were the modified Proctor to get our moisture density relationships, as well as strength testing, compressive and tensile, as well as flexural. Modulus, which is a parameter we need for pavement design, as well as flexural toughness and fracture properties. So the fibers we used, as I mentioned, we have 4 synthetic and we had 2 steel. The synthetic we had 2 that were smooth, one with a 40 millimeter length and one with a 58 millimeter length. And then we had 2 that were embossed, so they had some sort of surface texture to them, 48 millimeters and 50 millimeters. And then we had 2 steel fibers, one with a 60 millimeter length, and this was a hooked end, so at the ends we had a little hook, and then one that was helical in shape, so kind of think of like a DNA strand almost. And here's pictures of them. So the embossed, I don't know if it's visible from back there, but there is a surface texture to it. It's ridged and crimped along its length. Embossed 48 and embossed 50 are very similar, different manufacturers, but they're very similar in terms of their surface texture. And then we have the smooth ones, which is just smooth fiber with no surface texture. And then here we have the hooked ones, and they're glued together, which makes it easier for mixing in, and that glue comes apart during the mixing process. So during the shearing, it comes from a bundle of 10, 20, 30 fibers down into single individual fibers. And this is the helical one. So modified Proctor testing, this is our density versus moisture relationship. And the black line is a control, just a plain RCC with no fibers in it. And we see that all the fiber mixes are increasing the density, which is almost counterintuitive because we would expect fibers to hinder compaction rather than lead to higher densities. So we looked into this a little bit further. So what we did was we have our maximum density, and then from that we subtracted out the weight of the fibers, because for steel fibers the weight is rather significant. So we thought that just the weight of the fibers alone might be increasing the density. So in this last column here, we have the difference in density versus that of the control. And the density difference is after subtracting out the weight of the fibers. So we see that the synthetic fibers, these first four, are highly increasing our density, 1 to 3%, whereas the steel fibers are, about 0.5% on average, increasing our density. And this is what we thought was that this is fibers kind of lubricating the mix. So rather than aggregates interlocking with each other during compaction, the fibers getting in between there, and it's allowing the aggregates to arrange more preferentially. So our mix design, we held cement content fixed. This is about 475 pounds per cubic yard, a little bit lower than a typical concrete mix, which might be like 550 or 600. And then our aggregate content and water, those come from our moisture density relationship, and then our fibers. And here we have two different fiber dosages, 0.2% by volume and 0.4% by volume. So that way we can characterize the amount of fibers and their effect on the properties. So first testing we did was typical compressive strength testing. Compressive strength is the most widely used parameter for acceptance of a mix. The typical specification is that you need to achieve 31 MPa at about 28 days, which all of these far exceeded. And here we have our control, non-reinforced, and then all the fiber mixes. And we see that with the exception of the helical fiber, all the fibers are increasing or giving about similar compressive strengths, which is about opposite of what we would expect for fiber reinforced normal concrete. We would expect similar or even lower strengths. And for split tensile strength as well, we see that all fibers are increasing strength, with the steel fibers yielding significant increases in strength. So elastic modulus, another parameter we need for pavement design, we found that all fibers yielded similar results to the control. At the small strains of elastic modulus testing, we don't expect fibers to be engaged. They require a finite engagement length, so you have to strain the concrete so much that those fibers are actually being engaged and pulled on before they would contribute. So that brings us to the flexural performance testing. This is really where we can start to characterize the effects of the fibers. So how it's run is we have a 6-inch by 6-inch by 21-inch beam, and it's very similar to just the flexural strength test. However, what we do is we load this in displacement controlled. We have an LVDT here, and we displace it all the way up to 3 millimeters of vertical displacement, which is quite significant. And we can see that the crack is going to propagate up, and there's fibers bridging this crack all the way up until test ends. And it's actually really difficult to break one of these beams at the end of a test. And then from this we get a few main parameters. One of them is the residual flexural strength. So it's the flexural strength after a certain deflection. So after L over 150 or after L over 600, we have residual flexural strengths. And then an equivalent flexural strength ratio, where T150 is the area under this low displacement curve, and MOR is the flexural strength. So it's kind of a relationship of energy absorbance to the flexural strength. So here's a lot in one, but so we have a typical plot from each of the mixes, and we also have two concrete mixes, conventional concrete with fibers, steel fibers, and synthetic fibers. And what we see is that up here we have the three mixes with steel fibers, and these have significant residual strength all the way out to 3 millimeters over here. And the half shaded and half empty one is conventional concrete. So we see that it's behaving relatively similar to the RCC. And these loops here are actually individual steel fibers breaking. So during the test we would hear a loud pop, and that would be a fiber snapping in half, a steel fiber. So we run the test, we run it to its peak load, and then once it peaks, it drops off quite a lot for synthetic fibers, especially the lower dosages ones. But for steel fibers, it comes back to about half of its strength, and then it maintains those strengths or those load carrying abilities for quite a while. And we stopped the test at 3 millimeters because, one, that's what the standard says, and two, because in the field, even a deflection of 3 millimeters is quite significant, and it would take an extremely high load to achieve that. So practically, it's a limiting factor as well. So if we had an unreinforced beam, it would just come up here and it would fail. It wouldn't have any of this residual post-peak load carrying capacity. So the results from this is we get our residual flexural strength, and we get that flexural strength ratio. So if we look at the ones in orange here, we're comparing RCC with that smooth synthetic fiber to PCC, normal concrete with that same exact fiber. And we see that the behavior is pretty similar in terms of residual strength and the flexural strength ratio. These are two different fiber dosages, and it falls approximately in the middle of these two. So it's behaving similar in terms of the synthetic fiber, and similar with the steel fiber, similar properties. So from this, in terms of the flexural performance, we see that fiber-reinforced RCC has similar properties and similar behavior to fiber-reinforced conventional concrete, which has been studied in the literature quite more and is more documented. So we move to fracture properties. We tested this with the DCT, which was transition from asphalt over to concrete just by modifying some of the procedure. And what we do is we load it in tension, and then we measure the crack mouth opening. And the extension of this clip gauge is about 6 millimeters that we can accurately measure. So we test it out to about 5 millimeters. And even similar to the flexural strength test, even at 5 millimeters, the specimen isn't failed yet. It still has some residual capacity due to those fibers still bridging that gap and holding the specimen together. So this is comparing, again, an RCC and PCC mix with the same exact fiber at the same dosage. We see that RCC has a higher peak load, as well as a larger area under this curve as well than PCC. And the results from the testing, we get a few parameters. One is the critical stress intensity factor, which is a property of the material and its resistance to crack initiation. And then we also have fracture energy, and this is to 5 millimeters to normalize all the mixtures and compare them equally. And that's a measure of the material's resistance to crack propagation. So if we compare the green ones, this is just plain RCC and plain normal concrete. We see that roller compacted concrete has higher fracture properties than plain concrete on average. And the same is shown with the fiber reinforced ones. And in general, we see that the fiber reinforced mixes greatly increase our total fracture energy due to those fibers bridging that gap and holding the specimen together. However, the effect on K1C is not as large since crack initiation is very small strain behavior, and again, those fibers are not acting at that small strain. So some of the conclusions from our study is that the addition of these fibers to RCC, all the different kinds that we tested, significantly increased the split tensile strengths relative to the non-reinforced specimen. For compressive strength, it was about 50-50 whether or not it increased statistically or not. All the others were similar statistically. And then flexural performance, we see that fiber reinforced RCC behaves very similar to fiber reinforced concrete, FRC, for both synthetic and steel fibers that were tested. And for fracture properties, we see that they're greater than conventional concrete. And due to the similar or greater fracture properties of RCC, we would expect the fatigue properties of these materials to also be similar or greater. And there wasn't any significant difference between mechanical properties of the fibers that had embossing or surface texture versus those that were smooth, which was a rather interesting outcome of this study because one would expect a fiber that has some sort of surface texture to have better mechanical interlock with the matrix. However, they both showed very similar behavior. And the geometry, mainly the aspect ratio, the length to the diameter, had a large impact on fiber balling. We saw that the smooth 58, the very long and smooth fiber that didn't have much flexural rigidity, it had a lot of fiber balling in the mix. So it wasn't distributed nearly that well. And I'd just like to acknowledge Josh Chang and Douglas for their help with all the specimen mixing and testing, as well as Don Merrill for his help with testing, and of course IDOT for providing funding and feedback on this project. Thank you.
Any questions for Jeff?
How is the freeze-thaw cycle in comparison to your RCC with a huge drop in air rate?
It doesn't do so well in the lab. Previous research has shown that some mixes will pass, up to 300 cycles and maintain 80% of their modulus. Some research has shown that it fails. In the field, there's been reports showing that it lasts up in northern Canada for 30 years. So it's very sensitive to the mix design and proper construction. But if you get proper construction and it's going to last, it will most likely last in freeze thaw. Go ahead, Rebecca.
Thanks, Jeff.
Uh-huh.
I had a question in general about fibers. Are they used a lot in other applications that would be readily available?
Yeah, they would. Yeah, they would be readily available. They're used a lot in shotcrete, especially the steel fibers. And this fibers have been Professor Raisler's little guinea pig for his whole career. And it's difficult to convince industry to use them because if you show them strength properties of fibers versus no fibers are the same. So people don't want to pay more money to get the same properties. But what is commonly overlooked is the flexural toughness. So go back really quick. So if we account for all this area under the load here, we can reduce our thickness, even though our peak flexural strength is pretty similar between fibers and no fibers. But if we account for this ability to maintain its load even after deflection, then we can reduce our thicknesses, and therefore fibers become a very interesting alternative.
I'm just curious about the preparation of the spacer.
Mm-hmm.
You add the fiber in the concrete. How do you ensure that the distribution of the fibers in the concrete, like the steel or the other fibers, how do you make sure that's the homogeneously well distributed in that spacer?
So in the lab, we mix the specimen, or we mix the concrete for about 8 minutes, and that's just for a 2 cubic foot mix. In the field, they mix it for longer after they add the fibers. They mix it at the plant, and then usually fibers are added on site. So they'll throw the fibers in there, and then they'll give the truck another 30 revolutions or something. With RCC, it's usually mixed in a pug mill mixer. So how we would implement the fiber dosage into the actual mixing would be a good question. It would need to be a full-scale trial. Probably have to increase mixing time in order to ensure that it gets distributed well. Yeah, that would be something that's easily addressed in the lab, but would be more difficult to address in the field. You can run X-ray CT on it, on a hardened cylinder, but yeah, we don't have that.
Amanda,
Yeah, Amanda's done it, and
Right.
we contacted her about doing it, but it would be nice though. But from the test, we didn't notice any, like one cylinder had more fibers than the other in terms of its strength or whatnot. And the only fiber that gave us any issues with mixing was this fiber down here. It's very long, and it doesn't have flexural rigidity, so it kind of balls up together and it just gets stuck in a ball. And you could actually, when you pulled it out of the mix, you could just pick up a ball of fibers. So we'd have to kind of break it apart and mix it up a little bit longer.
I missed part of it, but early on you talked about load transfer with these fibers. With the RCC, is there set like saw crack joints, or just you let it shrink and crack where it wants?
So in the old days, or back in the 80s, they recommended that just pave it and that's it. Just leave it. You don't need to cut any joints. Now for most facilities are building with it, they do cut typical 15-foot joints or whatever. So we do have that nice defined joint geometry. However, over time, we don't know if that joint's going to open up, and RCC completely depends on aggregate interlock. So if you have a large joint, those aggregates aren't going to interlock and you have no load transfer, essentially. So these fibers will help bridge that and kind of hold it together.
All right, any other questions?
Let's just thank Jeff one more time. Our second presentation will be given by Hajin Choi, and he's a PhD student in the civil engineering department. He's working with Professor Popovics, and then Popovics' research interests lies in innovative testing methods for the evaluation of concrete performance, not necessarily for pavements. And his title of his presentation is a comparison of ultrasonic imaging techniques for full-scale reinforced concrete. Let's give him a round of applause.
Thank you. My name is Hajin Choi, and I work with Professor Popovics, and thank you for giving me this opportunity here. Today, I'd like to present about one of my topic, which is about comparison of ultrasonic imaging techniques for full-scale reinforced concrete. My outline of my presentation, I'm gonna introduce some new ultrasonic system, which is about some air-coupled and dry-coupled system. And second, their application to the lab scale, but full-sized reinforced concrete element. And I'm going to compare the following step about the imaging technique, which are the tomography and soft algorithms. For motivation of my research, for this research is about non-destructive tests, especially for ultrasonic imaging. The problem is the concrete. Concrete is pretty dense material, so we need to investigate some internal damages in the field. But for the ultrasonic method, it's quite limited in the field because of the coupling process. So now I'm using the ultrasonic method and also using some imaging methods to generate the internal images. There are two big challenges for this project. One is we need to have some meaningful signals through the full scale with very thick concrete element. And second, we also need to have some sufficient amount of data to generate this kind of internal images of concrete element. For the conventional method of the ultrasonic test, we have some very big kind of almost one number of reflected coefficient in acoustic reflected coefficient, which means almost all ultrasonic signal will be reflected back at the surface of the concrete between the transducer and the surface of concrete. So we use this kind of gel-type couplant to reduce that number and also give some more energy into the concrete. So this conventional ultrasonic method has significant limitation in the field. So we did not get quite good sufficient amount of data and also some good quality of data. So for here, I use the air-coupled without contact process in one side. At the other side, I attach the smaller size of the accelerometer for the through thickness measurement. And another method, I use the dry-coupled transducer array unit to measure the reflected waves at the one side. I'm going to compare those two methods in this work. Again, for the air-coupled and the multiple accelerometer setup, for the two-side method, I use the air-coupled transducer for the sender and multiple accelerometers for the opposite side. I use that accelerometer for the receivers. And I use the dry-coupled sender and array unit, this device. This device is dry-coupled, so we don't need any couplant, but it kind of generated the S wave. So I use this device for the one-side measurement system. Following that process, I use the two-sided tomographic algorithm based on transmitted P wave, and also I use the SAPT, which is about the synthetic aperture focusing technique, is based on reflected S wave. I applied the two different methods to the same specimen. This is my specimen. Its dimension is 36 by 28 inch, so pretty big concrete column. And before pouring the concrete, I embedded some artificially controlled defect. One is the styrofoam, and another one is a pre-cracked concrete prism inside. I'd like to point out the bottom part of this column because this part has the lesser rebar spacing compared to the upper part. So this part has a more densely embedded rebars there. This is the application of two different methods. For the dry coupled and array unit, I used the commercial device to onto just one side of the column. And for the air coupled and the multiple accelerometer for two-sided method, I made the automatic scanning frame. So I'm going to explain with a little video here. So the air coupled transducer was attached onto the automatic scanning frame here, and the transducer keeps sending the ultrasonic signals toward the column. And for the opposite side, I attached the accelerometer like here, and while moving and sending the ultrasonic signal, the accelerometer is measuring the ultra transmitted P wave signal in real time. So based on that measurement, this is a typical example of the P wave signals. When I zoom in this first part, and I can clearly see the arrival of the P wave, then from using that automatic scanning frame and some automatic procedure, I got about 4,600 signal for the one cross section. And when I'm using the dry coupled unit, this is a typical signal from this array unit. Because that unit has several transducer arrays here, this first part of this signal is not from the reflection, but it's from the direct S wave between two transducers. So based on that dimension, the distance between two transducers and the arrival of this direct waves, we can calculate the S wave velocity. From this unit and for one-sided measurement, I got about 1,600 signals for the one cross section. I'm going to talk about a little more about some imaging algorithm. First is about the tomography. Previously, I measured the through thickness P wave signal, and I got the arrival of the P wave at each position. And I assumed the wave distance as a straight wave distance. So we know the information of distance and arrival time of the P wave. Using two known information, we can calculate the velocity unit using some inversion method. So from the tomographic algorithm, what we have for the image is kind of P wave velocity map for the entire cross section. The soft algorithm is different. First, we need to calculate the travel distance between the assumed transducer positions. And then using that distance, previously we defined the S wave velocity from our measurement. Then with the velocity and the travel distance from the pixel to pixel, then we can calculate some corresponding time in signal plot, time domain plot. And in that time, we capture some amplitude and we map that amplitude onto that pixel. So the image from SAPT algorithm is kind of reflected S wave amplitude. So those are that's that is the difference between the two images algorithm, and the images are the different representative. I'm going to a little more discuss about some soft algorithm. First, we got the time domain, the signals from the transducer arrays. But remember, first part of signal is not from the reflection. It's direct signal between the transducers. So we need to remove some first part of signal for we only have the reflected signal. And then if we focus on just one part of the transducer, then we can kind of map it, some circular shape of the wave propagation to the concrete. And then we need to calculate the beam divergence of the transducer. It's about the apodization factor. Then we can multiply those to each other to have this kind of image. So this image represents some adjustment of the transducer and the wave propagation into the concrete. After we have this image for every transducer, and then we summed every transducer pairs, and we have this kind of image. This image represents some phase information as a blue and red color. So, but it's not clear yet. But if we use the Hilbert transform to remove some phase information, then we have clear red and blue color for the B-scan, some cross-sectional images. This is the typical B-scan, the cross-sectional image from the concrete, which is about red color represents some two rebars, and this red color represents some back wall. So we can identify some rebar position and the back wall using that kind of soft algorithm process. This is a result from about my test column. We have I showed three different cross-sectional images. So section 3 have both pre-cracked prism and the center styrofoam. So for section 3 images, both have some artificially controlled damages inside there. For the tomographic images, because that image represents the P-wave velocity, the lower color, the blue color represents the lower the velocity region, which can be the defect. And for the soft image, the highly reflected the signal is showed as the red color. In soft image, interestingly, we can see some rebar position near the surface, but I'd like to point out some dark region very near the surface, because we removed the first part of the signal, because that's not from the reflection, it's from the direct S wave between the transducer. So we kind of lose the data at the beginning. So we call that is the kind of blind zone for this method. For the tomographic image, we also have some limitation on near the receiver part, because we have some limited numbers of the receiver part here. Then we have some empty space for inversion algorithm. So we don't have any number for that, then we can see some artificial ray path from the images. But I can say both imaging algorithms can capture some artificially embedded defect from the full-size concrete, the element. And this image, after I generated the cross-sectional image, I stacked the image in vertically and cut the image in vertically. So this image is kind of this vertical section of the column, and its image is better for showing the defect here. So first two should have some the void in the upper part, and another void in the bottom, and pre-cracked concrete prism on the bottom center. For the tomographic image, the blue color represents all three the embedded defects. But interestingly, the soft image has higher reflection at the upper part, but no reflected signal from the bottom part. That's because in bottom part, we have some lesser, very dense rebar, the embedment inside the concrete column. So the reflected signal was quite limited to have that information in deep side of the concrete. But in other case, when the near surface of the column where the rebars are embedded, for the tomographic image, it cannot show any information of rebar because the P wave, the through thickness P wave, just ignore that the embedment, and the image cannot generate the information. But for the soft images, because of it's about the reflection, so high reflection was made from nearly embedded rebar. So we can see some information of rebar from the soft algorithm. I a little bit investigate more about some visualization for my tomographic images. So I use some computer vision method to generate the external images of the concrete, and I marked where I embedded the defect. And so using this 3D, the virtual environment system, we can recognize where the defect is from our tomographic images and also some external 3D images. So this is a result of the tomographic data. So this is the picture of before deploying the concrete, and this is the design, as is design of the concrete column, and the marked the artificially embedded defect position. And the blue color, the well match with the location of the defect, and in 3D images also show some blue color where I designed the position of the artificially embedded defect. For the soft images, from this, I used the commercially provided the software, and now I had some question here, because when I used this just one-sided method, one-sided plane of the column, then I lose some information. But here, where we should have some defect in near surface styrofoam in this side. But previously, because of highly embedded the reinforcement on the bottom, we lose the data here. So what about I use this section, then I can clearly recognize the vertically embedded styrofoam inside. So from this image, there is some shadow zone beyond that the highly reflected the rebar layer. So from the image, we need to know this imaging algorithm have some kind of limitation. Then image is not about the reality about the infrastructure. Image is about what we measured, and if we measured not enough information about some embedded defect, then image cannot represent the right reality of the infrastructure. But now I have one more question here. We can see clearly in vertically embedded the rebar, but not about the transverse rebar. So I simply changed the orientation of the device. Previously, I used the horizontal scan, but now I'm using the vertical direction of the scanning. Then I can see some horizontally embedded rebar, and on the bottom part, there are high reflection from the rebar. This is because this device has the 4 transducer in one column, and this device saves just one signal from the one column of the transducer. So if we have some rebar perpendicular to the device direction, then each 4 transducer may have the highly reflected signal constantly and save the average saved data have some high reflection and also about some information of this rebar. But if the rebar is embedded parallel to the device orientation, then some of the transducer missed some signal, then the average, the saved data has a less reflected signal than after generating the image using the SAPT algorithm, then we don't see clear information about this kind of rebar information. That's why when I use the vertical scan from the column, then I can clearly show the hoop rebar inside the concrete. This is back to the comparison study. This is the comparison between two algorithms. So for the tomography reconstruction, we show some full information about the defect, but it requires a two-sided access to the structure, which is may not practical for the specific infrastructure like pavement. And also, the SAPT algorithm always good for the one-side scanning, but it has some limitation for the shadow zone and some blind zone. So finally, I'd like to conclude the imaging method, ultrasonic imaging method. Now we can use some development of the ultrasonic method based on the hardware improvement, and we can generate the internal images from the full-scale concrete element. But we need to recognize what the image represents. Again, if the signal, ultrasonic signal, cannot capture the right information from the specimen, then image cannot represent the right information to you. That's my conclusion, and I'd like to thank you my support funding, especially for IDOT. Then I'd like to thank you all, and I have now room for the question. Thank you.
Any questions for Hygiene? Go ahead.
Very nice work. So I have some questions regarding the tomography method. So there's another reconstruction method, which is the inverse red, right?
Yeah.
So did you try that method? Because that one should be faster than the algebraic.
Yes. As you know, the filter back projection method requires the continuous measurement.
Yes.
From every angle.
Okay.
Then, which I don't in this problem. So I tried to use that algorithm using some interpolation of about the empty data, and it worked really well. Actually, some similar images and with the best algorithm. But for me, it's kind of interpolation, so kind of fake data.
So what's the computation time of that algebraic reconstruction?
Algebraic reconstruction for the one cross-sectional image is, I remember, just about 1 minute. As for when I use the filter back projection, it's about just a few seconds.
I see. Yeah. And what's the discretization steps in the image domain? The pixel.
Pixel
resolution, yes.
It depends first, it should depend on the number of receiver and the number of the transducer position. So my transducer position was about 0.1 inch, but for 36-inch plane. So image resolution was 360 by 280.
And another question, so what's the waveform of the air-coupled and dry-coupled ultrasonic, and what are their frequencies?
Both are about the 50 kilohertz, because for the concrete application, we need to reduce the frequency, center frequency, to avoid some scattering effect. And also for the P wave generation, and because of the air-coupled transducer should generate enough energy into the air to ignore some large number of the reflection coefficient, I use the 16th cycle of and so narrow band of 50 kilohertz signal. But the dry couple signal is kind of impact. So
it's a pulse.
yes, it's a kind of impact test.
Thank you.
Question about that? I have a question. What was the specific motivation or application of IDAT from this study? What were they looking at?
First about the MIRA, the commercial device. So we'd like to apply that device to the investigation of the delamination of the pavement, and also possibly the distribution of the crack. But for my experience, if we have some clear delamination
in the pavement, then this device really will detect that the delamination, because that delamination makes high reflected signal back. But if we have some kind of randomly distributed crack, then we cannot have some constant reflection from the crack zone. Which means we cannot generate the images as good as what we expected.
Outcome is negative.
yes.
Okay. Yeah. Any other questions? Well, there's no other questions. That concludes our Ken seminar presentations today. Thank you all for coming. Let's give our presenters a moment.